In 2019, researchers conducted an extraordinary experiment that brought the mind-bending implications of Wigner's friend out of the realm of thought experiments and into the laboratory. Their results not only challenged our classical understanding of reality but also forced us to reconsider the nature of objectivity in science. Let's dive deep into what they did, what they discovered, and why it matters. Wigner's friend, proposed by Eugene Wigner in 1961, is a paradox that examines the role of observation in quantum mechanics. It suggests that two observers can experience completely different realities depending on their frame of reference. Here's a quick recap. 1. A quantum system, like a photon, exists in a superposition of states, e.g., horizontal and vertical polarization. 2. A friend inside a closed lab measures the system and sees a definite result, collapsing the superposition. 3. An outside observer, Wigner, treats the friend and the lab as part of a larger quantum system, which remains in a superposition until Wigner observes it. The paradox lies in the fact that Wigner and his friend can have conflicting accounts of reality. The 2019 experiment put this paradox to the test. A team of physicists, led by Massimiliano Prati and colleagues at Heriot-Watt University in Edinburgh, designed an experiment to simulate Wigner's friend using quantum systems. Their goal was to test whether two observers could genuinely experience different realities. The setup included 1. Quantum systems. The researchers used entangled photons to represent quantum states. Entanglement ensures that the state of one photon depends on the state of the other, no matter how far apart they are. 2. Two observers. The experiment involved two pairs of observers, one inside the lab, simulated by measuring devices, and one outside the lab. These were observer A and friend A. Inside the lab, friend A measures the state of a photon. Observer B and friend B. Observer B later examines the results of friend A's measurement from the outside. 3. Measurements. Inside the lab, friend A measures the photon's polarization, e.g., horizontal or vertical, and records the result. Observer B, outside the lab, treats the entire system, including friend A's measurement, as a quantum system and performs their own measurement. The researchers asked, can the results of these two observers, friend A and observer B, both be valid, even if they conflict? In other words, can two realities coexist? The results were astonishing. The researchers found evidence that 1. Observer-dependent reality. The outcomes observed by the friends inside the lab and the observers outside the lab could not be reconciled into a single, objective reality. From friend A's perspective, the photon's polarization was definite, it had a specific state. From observer B's perspective, the photon and friend A's measurement were still in superposition, meaning no definite state existed. 2. Breaking objectivity. The experiment showed that the idea of an objective, universal reality, where everyone agrees on what is true, does not hold in the quantum realm. Instead, reality may be fundamentally observer-dependent. This experiment has profound implications for physics and philosophy. 1. Objective reality is an illusion. In classical physics, we assume that reality is objective and exists independently of observers. The 2019 experiment suggests this is not true for quantum systems. Instead, reality is inherently subjective and depends on the observer's frame of reference. 2. The measurement problem deepens. The results highlight the unresolved measurement problem in quantum mechanics. If different observers experience different realities, what actually causes the collapse of the quantum wave function? Is there even a collapse, or is it just a convenient interpretation? 3. New challenges for quantum interpretations. The findings challenge long-standing interpretations of quantum mechanics. Copenhagen interpretation. If measurement collapses reality, whose measurement counts? Many worlds interpretation. The experiment aligns with the idea that multiple realities can coexist, as each observer experiences a different branch of the multiverse. Relational quantum mechanics. This interpretation gains support, as it argues that reality is relational and depends on interactions between observers and systems. The 2019 experiment represents a shift in how we approach philosophical questions about quantum mechanics. These are no longer purely theoretical discussions, scientists can now test them in the lab. While groundbreaking, the experiment is not without its limitations. Simplified models. The observers in the experiment were represented by measurement devices, not conscious beings like Wigner and his friend. Scalability. Extending such experiments to larger systems, e.g., involving human observers, remains a significant challenge. Interpretation dependence. The results depend on how you interpret quantum mechanics, and no consensus exists among physicists. Despite these challenges, the 2019 experiment is a pivotal step forward in understanding quantum mechanics and its philosophical implications. The 2019 Wigner's friend experiment is a fascinating reminder of the strangeness of the quantum world. It challenges us to rethink fundamental questions about reality, observation, and objectivity. Are we all living in our own quantum bubbles of reality? Does the universe itself exist independently of observation, or is it shaped by those who observe it? These questions remain unanswered, but one thing is clear: quantum mechanics is not just a set of equations, it's a window into the very nature of existence. As experimental capabilities continue to advance, we may one day uncover whether reality itself is as fluid and subjective as Wigner's friend suggests. Prepare to have your mind blown. The universe may be stranger than we ever imagined.